Hi, welcome back to the stream. So in this stream, we are going to talk about double faults. So in our last stream, we have talked about what are CPU exceptions, and we have written a simple CPU exception handler, that is a breakpoint handler, in the last video. Today, we are going to talk about what is double fault, how to test a double fault, and how to write a double fault handler for our operating system. So let's get started. A double fault is nothing but, as we have discussed, we have also touched upon this in our last video, that a double fault is nothing but exception which occurs in the process of invoking another exception. So basically, just take an example of our previous example wherein we were demonstrating breakpoint exception. Now consider a case that a breakpoint exception occurs, but consider a case where we don't have a breakpoint exception handler. So in that case, what will happen? CPU will know that a breakpoint exception has occurred, but and then it will go to our interrupt descriptor table also. It will search for the entry, and just take an example that we don't have a breakpoint exception handler at the place. So what it will do, it will try to call, or it will try to go at that particular function pointer location, but the function pointer is not present. That means it is not initialized, it is 0, and CPU will try to call that particular 0th memory location, and in this particular process we will get another exception, that is a general purpose exception, that is a paging exception, or some another exception. And this whole scenario constitutes a double fault. So double faults are nothing but faults which are occurred in the process of calling an exception handler or an interrupt handler. So here they are talking about a very simple example wherein we have our code running, that is we have our start function, we print hello world. We do interrupt initialization also, and then we are going to dereference some memory location which is not present, or some memory location which is not to be dereferenced, and we are going to write something on that particular memory location, and then let's see what happens. So this will trigger our page fault, and since we don't have a page fault handler, our double fault will get triggered. But now in the current scenario, before executing this code, we don't have double fault handler also not in the place. So what it will do, it will execute a triple fault, and triple faults, as we discussed, they are non-recoverable. Our whole system will reset. So we are not going to try this particular example. We will first write our double fault handler and then see what actually happens. So let's go to our repository. So this is our code, and this was the last committed code. And here we are going to write now double fault handler. My double fault handler. So here this will be again same. Only the difference will be here we'll name it double fault handler. I think what does it takes? Double fault handler takes the stack frame and an error code as well. That means these are the handlers which takes error code also with them. So we'll pass the error code as well. Let's copy this thing and paste it over here. We'll have interrupt stack frame and an error code, and here we are going to just print double fault occurred. This is the stack frame error code. This one also we're going to print. So this is our double fault handler. This is our breakpoint exception handler, and here we are going to initialize this handler. IDT dot double fault dot set handler function, and this we will give it double fault handler stack frame and error code. We are not going to call it, we are just going to pass it as an argument. So this is our double fault handler. Now here we are getting an error that double fault handler arguments to this method are incorrect. But okay, let's see what exactly these guys have done. Everything is same. Actually we are panicking over here. We are not printing, we are panicking because double fault should panic. So let's exception double fault stack frame, and that's all. And the definition is also same, interrupt stack frame error code, which returns none. Okay, let me do this. I don't want this calendar. Okay, I want the app store also. So now it is clear. It should not return anything. I think now the error is gone. Yeah. So yes, our double fault handler is now in place. And now let's try this thing. Let's try to dereference. Control C, and here we are going to dereference a particular page. Oh, it's already there, so let's just uncomment it. So we have a breakpoint exception. Don't use this, and let's build this thing. So we'll just do cargo boot image. And this should build it, and we just need to do cargo run, so we can see QEMU. Yes, so in this emulator you can see panic occurred because of panicked at source main21 misaligned pointer dereference. Address must be of multiple of 4, but it is deadbeef, so that is what it was expected. But we haven't got the stack frame. Panic occurred at exception double fault, and it worked. The CPU tries to write deadbeef, which causes a page fault, and that's all. Let's see why the print statements are different, because we panicked exception double fault. Oh, okay. Let's do this in this way only. Control C. I think this time it will show the required exception message. Okay, I'll just close this, and once again we will do cargo run. Yeah, and this time we have got the expected message on the emulator as well. So we have printed out the stack frame, and we are also printing a panic occurred because of this particular reason. So this is how we have written our double fault handler, and it is also working. But now let's look into some corner cases. So now consider a system wherein you have particular OS, and this OS is running in a predefined stack frame. There must be some stack frame allocated to our operating system, right? Exactly, it is if we talk about in layman language, there is a physical memory on which our operating system is running. Now let's assume that this physical memory is being managed by our operating system by using different memory management techniques. We'll dive deep into it in the later stage of time. But now, since this is a bare metal, or we are just having bare minimum things, let us have an example where if we have a program written on this operating system, and that program is non-exhaustive, it is calling, it has some recursive calls, and because of that recursive calls, the stack frame goes on increasing and increasing and increasing, and there comes a point wherein, the physical memory is exhausted for the operating system as well. So operating system is not able to provide any extra memory for our program. So at that particular point, what happens is we will end up in a page fault. And in such scenarios, in the case of page faults, then our page fault handler will be called. But since we don't have a page fault handler in place, so what it will do, it will call a double fault handler, and this double fault handler exception function will be invoked. But now consider a scenario where already all the available memory is being utilized by the operating system, and in such cases the operating system is also not aware, is able to give you the space for your exception handler. So in such scenarios, what we need to do is we need to make sure that in any situation our double faults and our exceptions are in place, and no matter what happens, they are being getting called anyhow. So so in order to do this, what we do is we use stack frames. So we what we do is a stack frame is meant for, we divide the stack frame, and this initial or some part of stack is reserved for this exception handling, interrupt handling, or some functions which are privileged. So let's go down. What they are saying is causes of double faults. Here they are discussing what is the exact causes of double faults. So as we have discussed, it is nothing but the point where, in the process of calling an exception, if another exception occurs, then it is a double fault. And now we are discussing about kernel stack overflow. So this can easily happen by using such scenarios wherein, we have a function which is calling itself unlimited number of times. So this, what it will do, it will utilize all of your stack, available stack. So in this case, what will happen is we will not be able to call our double fault also, or any other exception also. So what the solution is, we have interrupt stack table and task state statement. Now these two things are very specific to x86 architecture. So what they are saying is TSS, that is task state segment, is used to switch your task whenever an exception occurs, and it switches your task state segment. That means it switches your stack to to a good stack wherein, corruption has not been occurred. So basically there is there is an end, there is a, what do we say, there is a limit of stack which can be given to an operating system. So how does that operating system detects that this is the end of my stack? They use basically a end page, or what they are using, there's a term they are calling it. Let me find that term. It is possible to detect stack overflow. The page is guard page. So what an operating system does is it maintains a guard page, and this guard page, nothing but it shows the end of your physical memory. In such scenarios wherein we are calling a function exhaustively, operating system will go on to provide the stack unless it reaches the guard page. Once it reaches the guard page, again it will generate an exception, and in this way we are landed into an double fault exception handler. But since we don't have any stack left, we cannot call double fault also. So in order to prevent this phenomena, what we are going to do is we are going to keep a part of stack available for our exception handlings. So in order to do that, we are going to use task state segment, and this is a process wherein we keep some of the stack available no matter what happens for our interrupt handlers and exception handlers. So how to do that, this we are going to see. So basically this is the structure of task state segment. It has a privilege stack table which is being used for privilege stack. It has an interrupt stack table, and it has some IO base map addresses. But in our case, we don't have any privilege mode till now. We don't have a kernel space mode and user space mode. So that we will just use interrupt stack table for us for now. And in order to create a TSS, we will again create a new file or a new module in our code, and in that code we are going to handle all this thing related to TSS. So what we are going to do is, in task state segment, we are going to add an entry of our double fault handler, or we are going to add an entry of our stack which is being reserved for our double fault handler. How to do that? That is being shown here. So what they are doing is, again, everything is lazy static because everything needs to be available for all the modules. That is, everything needs to be a global static thing. So that's why we are using lazy static. In this line we have created a task segment new, then TSS, there is an entry of interrupt stack table. Now interrupt stack table is of type U64, and there are 7 entries that we can provide for our interrupt stack table, and we are just going to provide the 0th entry for our double fault index or for our double fault handler. So what we are going to do is, double fault, that is interrupt stack table's 0th index is nothing but is equals to, we create a stack size that is 4000 into 5, and then what we do is we create a static a global static mutable array of this particular size, stack size. This we get from virtual address. We get the start address from this virtual address module, and we calculate a stack end, and finally we return a stack end to this particular index. That means this entry is being initialized to our stack end. Why we are initializing stack end? Because in x86 stack grows downward. That means it grows from top to down. So let's just directly copy this code into our repository. So we are going to create here one more file that is called as gdt.rs, and here we are going to paste this thing. We have virtual address. Virtual address takes care of creating some virtual address from our stack, whatever we have created, or for some virtual address for our stack, and that virtual address can be our start address, and from that we can calculate end address. So this is being available now over here. You can have pub mod gdt, yes, and then this gdt is created. But in order to load this gdt, what they are saying is, there is again one more thing we need to take care. So what is that thing? That is global descriptor table. Now I haven't spent much time in checking out what a global descriptor table is, but here is already a link provided, and it is a very exhaustive link which talks about what a global descriptor table is and what is basically significance of global descriptor table. So I can give you an overview that global descriptor table is used whenever we want to switch from a kernel mode to a user mode. So what they have done is, what they're talking over here is, before memory management came into picture, that is paging was, before paging came into picture, this was the thing which was taking care of allocating different stack to different programs. So, or this was the thing which was being used for the memory management for different processes. So let's use this, and because till now till this point we are not we have not introduced paging for our operating system. So let's see how to do that. So again, we are relying on x86 crate. We get the global descriptor table and descriptor into the picture. So what we are doing over here is again we are using lazy static because it has to be a global mutable state. And first of all, we are getting the instance, and in that GDT we are adding an entry of a kernel mode segment, and then we are adding an entry of TSS segment. That is, we need to provide the stack. We need to give it the information of segments. So here we are giving it there is first is kernel mode segment, and another segment is your TSS segment. Now this TSS segment is nothing but our this one, where we have already said that TSS entry, there is a TSS star, that is a TSS global variable is there, which has the entry for our double fault index. So in this way you see that once we have defined a stack in our TSS, and that TSS entry is now we have provided to our global descriptor table also. So in this way we can make sure that our our double fault handler will never crash in the case of kernel overflows also. So we'll go here and we'll just paste it. So this let's or what I want to do, Control X, and I will put it over here. Sorry, and we'll just do Control Shift I or Control Shift I. Yeah. So we have initialized our GDT. Now in order to load the task segment, we need to just do GDT dot load, and finally in our init function we'll be doing GDT init and then interrupt init. So let's do pub fn GDT init. What this function will do? GDT dot load. So this will automatically load the task segment or TSS segment, and TSS will be created over here. So this will be taken care. And now in our lib.rs or in our interrupt.rs, init IDT or our lib.rs, where init is there. Where is the init thing for us? Let's go to so this is our init function, interrupt init. So first of all we're going to call GDT init, and then after that interrupt init. So here we'll be doing GDT init, okay, and then init IDT. So this is the way we are going to write exception, or this is the way we are going to write we need to write exception for default double fault handlers. Now in final steps, what we are going to do, we are going to demonstrate a double fault exception. So for that what we are going to do is GDT segments are not yet active because segment in TSS. In summary, we need following things. We need to reload the code segment register, load the TSS, and update the IDT entry. So for the first two steps, we need code selector and TSS selector variable in our GDT init. So that we are going to do it. We need a segment selector. That means segments needs to be provided. So let's have this thing. Code selector is also type of this, and this is also exactly okay. Let's. So here what we are going to do is yeah, we copy this and then we go ahead and paste it over in our gdt.rs. So this is how we are going to actually write our GDT global descriptor table. and this will be our initialization code. Okay. And we reload the code segment using cs.set registers and load TSS. And similarly, we need to do it for our interrupt descriptor table also. So we'll just copy this code, Control C, and in our interrupt.rs, we will put it somewhere here, where in our interrupt descriptor table, because at the end, interrupt descriptor table is going to initialize everything. So this was our breakpoint handler, and this is our double fault handler, and set stack in that we have also set stack index as double fault ist index, and this we need to define somewhere. Is it defined? Yes, it is defined to be 0. So this is how we are going to write a double fault exception handler. So the crux of this particular video is that in order to, double fault exception handlers are nothing are simple handlers only, like this one. But in order to make sure our kernel stack, in order to make sure of that corner case where our kernel stack can also overpass, or it can also overflow, in order to handle that corner case, we need to make sure that there is a stack frame, or there is some physical stack which is still available in order for our exceptions to execute. And for that we need to use TSS and global descriptor table. And now finally we run our stack overflow test as well. So let's call a function in our start or our main.rs. So this was our one thing, but let's call a function, define a function fn stack overflow, which calls itself stack overflow, and we call stack overflow. So what this will do, it will allocate the stack again and again and again, and finally guard page will be hit and our exception will be called. So the exception, yeah, so you see there is a panic because of this particular line in interrupt.rs, that is double fault, and this is our stack frame. And yeah, we are able to catch our double faults as well. Although I am not sure why my program is panicking at interrupt.rs33. Let's go to that particular line, interrupt.rs33. What am I going on 33? Panic. Okay, this is the line of panic handler. But okay, I think it's still working, and we are able to get the double faults thing, double faults being handled by our operating system in a better way. Even if there is a what we say kernel overflow is also there, then also we are able to catch our double faults. In this case, what happens then? It should handle it gracefully. Just do Control C and again cargo run. Okay, in this case also it is saying that interrupt.rs line number this because it is panicking. I think this makes sense. No need to worry. And that's all for this video. Stay tuned for the next thing. In the next post, we are going to handle actual hardware interrupts, wherein we are going to write something with the keyboard, and those later should be printing on our console. So that is the functionality we are going to add for our operating system. Till then, bye bye.